Hello, good morning, Bulldogs. We are continuing our study of calculus. We're in chapter 2. This is chapter 2.6, tangents, velocities, and other rates of change. So in the previous section, you learned all about continuity. In this section, we're going to talk about how we can use the idea of limits to create rates of change for a function, but also for moving objects, like in applications such as velocity. So I am in your chapter 2 notes packet. We are on page 12 of that notes packet. I'm going to hop over the bell work question. That's just reinforcement of what we have done in the past. And what we're going to look at right now is definition number 1, which is the tangent line to the curve y equals f of x at the point P of a f of a is the line through P with this slope, provided that the limit exists. Okay, what are we talking about here? I'm going to draw a little curve. And let's say my curve looks like this. And I am going to call this point A, which means that this point's y-coordinate would be f of a. And its coordinates would be a f of a. And then way over here, I'm going to put point x. And so its corresponding y-coordinate would be f of x. And this point would be x, f of x. And what I'm looking for is a representation for the slope between these 2 points. So if I were to consider that slope, we're looking for a slope formula, which would be y minus y over x minus x. So if I'm talking about the slope of the secant line, which I'm going to call m, but I'm going to give it a little subscript of SEC for secant, I'm just finding an old-fashioned traditional slope, y minus y over x minus x. So f of x minus f of a over x minus a. But we know from previous sections that the closer and closer and closer that I make x to a, these little secant lines start to resemble my tangent line slope. And so what I'm really trying to do is find the slope of a tangent line, which we know we can't find with a single point. But I'm going to look at the behavior or the limit of the slope of the secant line in order to approximate the slope of the tangent line. So how do we find that slope of the tangent line? We're going to take the slope of the secant line and we're going to say that we're going to find the limit of that slope of the secant line, f of x minus f of a, all over x minus a, as x gets closer to a, so as x approaches a. So we're taking this idea of finding the slopes that we did back in the beginning of chapter 2, and we're combining it with our concept, our understanding of limits. And now you know how to evaluate limits algebraically. So we're taking all of these little lessons and combining them today to generate a rate of change. And that's essentially what a slope is. It's a rate of change. All right, so what's the difference between secant slope and tangent slope? The tangent slope is going to be a limit. The secant slope will be a traditional slope. So I'm going to call this m with a little tangent as a subscript. So we've got an example here. Using definition number 1, find the following for the function y equals x cubed. So write an expression for the slope of the secant line through the point 2f of 2 and x f of x. Well, first of all, let's actually define what these points are. So P would be 2, and if I substitute 2 in, I would have 8. And Q would be x, and if I substitute x in, we would have x cubed. So we're looking for an expression for the slope of the secant line. So I'm just going to set up a slope formula. Y minus y over x minus x. So y minus y would be x cubed minus 8 over x minus 2. And we now have an expression for the slope of the secant line. Part B is asking us to write an expression for the slope of the tangent line at point P. Well, what do we now know is the difference between the slope of the secant line and the slope of the tangent line? The function is the same. It's just that my tangent line will force x to get closer and closer to a. So I'm going to take this secant line slope, x cubed minus 8 over x minus 2, and we're going to set this up as a limit as x approaches a. What is a on this problem? Well, folks, a is that 2 value, that fixed point. That 2 was a, and this was my f of a. So as x approaches 2. So we've just written an expression for the slope of the tangent line. And then the last question says, find an equation of the line tangent at point P. Well, what do I need to write an equation? I need a point and I need slope. Well, I already know my point. It's 2, 8. That's my fixed point. And I need to find a numeric slope. What we have here is a formula for slope. So what I need to do now, and oh, I forgot to write my little label on here. What we need to do now is actually find what the slope is. Back in the beginning of chapter 2, we did this by looking at the function and using our table feature on our graphing calculator. Now we have the tools to find this algebraically. So we want to evaluate this limit. And I know what I always try to do first when I evaluate a limit is, can I substitute 2 in? But if I substitute 2 in, we have a 0 in the denominator, so that is not going to work. That's an undefined function. So what I'm going to do instead is I'm going to try to factor and simplify this expression. So we would have the limit as x approaches 2, and in your numerator, this is a difference of cubes. So in the numerator, that's going to be a binomial times a trinomial. You remember this from last year or the year before. Binomial is going to be x minus 2. Trinomial is going to be x squared. Our sign changes to a plus. Multiply these two terms, 2x, and then square the last term. And then my denominator is an x minus 2. And sure enough, what are we seeing happen? My x minus 2's are canceling. And I am left with the limit as x approaches 2 of x squared plus 2x plus 4. I've just eliminated the issue, which was when I substituted 2 in, I was getting a 0. So now I am ready to substitute 2 in. So 2 squared plus 2 times 2 plus 4. So 4 plus 4 plus 4 is 12. What was this limit calculating? Don't forget, this was calculating the slope of my tangent line. So I now know that that slope of my tangent line is 12. And I now can find my equation of my line tangent at point P. So y minus 8 equals 12 times x minus 2. You can leave it like that. No need to turn that into slope-intercept form unless somebody asks you to do that. Okay, so this is what we call definition 1. It is very wonderful to use. However, sometimes the expression that you get when you create this function is not something that we can algebraically simplify. So there is an alternative definition that will always work for us. And this alternative definition is what your book calls definition 2. So when you're doing your homework, you have to pay very close attention. The directions on some of your problems say use definition 1, and some of them say use definition 2. Okay, so where is this coming from? I'm going to draw another picture here. And I'm going to start with A, just like we did before. But now I'm going to make this other point B. I'm not going to call it X. I'm just going to call it a point further away from A. How far away from A is it? Well, I'm going to add H to this, which means that an expression for this new x coordinate would be a plus h. So this coordinate would have a y value of f of a, so that would be a f of a. And this coordinate would have a y value of f of a plus h. And that point would be a plus h, comma, f of a plus h. Okay, so what I'm trying to do first is I'm going to start by creating an equation of the secant line, just like we did on the page before this. And then I'm going to use a limit to actually represent the slope of the tangent line, because that's what I really want to find, is the slope of that tangent line. So for my slope of my secant line, I'm going to set up y minus y over x minus x. So that would be f of a plus h minus f of a all over a plus h minus a. And you can see that my a's are going to cancel, and what I am left with is just the expression f of a plus h minus f of a all over h. That represents the slope of my secant line, but now we know that in order to find the slope of the tangent line, all we have to do is set up a limit. Now, what am I going to set up my limit as? On the previous question, we said that we wanted x to get closer and closer to a, so that these secant line slopes approached the approximation of the tangent line slope. So we had x approaches a. Well, on this one, I also want a plus h to get closer and closer and closer to a, so that these little secant line slopes get closer and closer and closer to what that tangent line looks like. So if I am squeezing these 2 points closer and closer, what is happening to h? H is getting smaller. In fact, we're going to allow h to approach 0. So that's how we're going to set up our limit. All right, so let's take a look at our very first example. Find the equation of a tangent line to the parabola at the given points and then sketch it. Okay, so what we're looking for here, in order to find an equation of a tangent line, I need a point, which I have right here. But what I'm missing is the slope. If you wanted to start setting this up, you certainly could. Y minus 33 equals m times x minus 3. But now I've got to find the slope of that tangent line. And we're going to dive straight into the limit definition, because that would be the slope of my tangent line. So when you are using this formula, which you probably recognize from earlier in chapter 1, the a value represents your fixed point. So in this problem, my a value is the 3, and the f of a value is the 33. So I'm going to start by using this formula, and I'm going to set this up as the limit as h approaches 0. Remember, this is the slope of the tangent line here. As h approaches 0, of f of, instead of putting a plus h there, I'm going to put the 3 in. So f of 3 plus h minus f of 3 all over h. And now I am going to expand this expression. What do I mean by that? F of 3 plus h is really the function f of x with a 3 plus h substituted in. It's really like a composition. So I am going to replace 3 plus h into each of these x's. So this is my front end here. So I would have 3 times 3 plus h squared plus 2 times 3 plus h. I'm going to close that off. This represents f of 3 plus h minus f of 3. Now, normally I then plug 3 in, but I already know that when 3 gets plugged in, my answer is 33. So you can just grab that 33 right there. Save yourself some time. And that is all over an h. And now we are going to simplify this expression. So let's expand 3 plus h squared. So that would be 9 plus 6h plus h squared plus 6 plus 2h minus 33 all over h. Let's keep going. So we've got 27 plus 18h plus 3h squared plus 6 plus 2h minus 33 all over h. Let's clean this up a little bit. 27 plus 6 is 33 minus 33. Well, those all cancel. And I'll give you a little hint. You're going to see numbers cancel. You're going to see expressions cancel when you work these. So what am I left with? 18h plus, oh, we can combine those two. So 18h plus 2h is 20h. Let's go ahead. We'll just simplify this as we go. Why not? So we've got 20h plus 3h squared all over h. Now, we're not done yet. We are actually evaluating a limit. So what am I going to do next? I'm going to simplify this expression by dividing both of these terms by h. I'm going to come over here and use this space. So we would have the limit as h approaches 0. 20h over h is 20. 3h squared over h is 3h. And now I can evaluate this limit. Earlier, I couldn't substitute 0 in because that would give me a 0 in the denominator. So 20 plus 3 times 0, which leaves me with 20. All right, so what did we just find? We found the slope of the tangent line to be 20. So we can go back up to our equation that we initially set up. Y minus 33 equals 20 times x minus 3. Okay, so the whole point of this problem was to find an approximation for the slope of that tangent line so that we could generate a line for the tangent line. So what would happen if I was then asked to do this question again, but change a to 1? I'd have to start all over again. And so my initial limit would be f of 1 plus h minus f of 1 all over h. And I would expand that whole thing out with the 1 in place of the 3. And then whatever f of 1 is would get replaced here. And the process would be very similar, but with different numbers. And then what if I followed up and I said, hey, I'd like you to do that again, but with a different one. Not x equals 3, not x equals 1. Let's do it with x equals 6. And you're repeating this long limiting process. And sometimes in math, we want to work smarter, not harder. So what we can do instead is we can find tangent lines using a in place of a fixed number. And what that allows us to do is come up with an expression. It won't be a numeric value at the end yet. But in place of 3, we would actually have an a, the original a that is in our definition. And we would wind up with an expression that represents the tangent line. And once you have an expression that represents the slope of the tangent line, then you can plug any values in that you want for a. This is very helpful, especially in applications like velocity or rates of change, where you know that you're using multiple a values within the same problem. So I'm going to take this exact same example, and I'm going to work this keeping a in my problem. So we're going to start with this definition from way up here. So we're going to have the limit as h approaches 0 of f of a plus h minus f of a all over h. And what this is finding for me is my slope of my tangent line. And now I'm substituting a plus h into my formula. Remember, I'm using the same formula as I was before. So my next step would be the limit as h approaches 0 of, and in place of x, I'm going to put a plus h. So we would have 3 times a plus h quantities squared plus 2 times a plus h minus f of a. So now I'm going to substitute a into this function. So minus 3a squared plus 2a. And that is all over an h. Okay, now I'm going to simplify this by expanding out and adding like terms. Just like we did earlier with numbers, but we're trying to work smarter. So we're left with a squared plus 2ah plus h squared plus 2a plus 2h minus 3a squared minus 2a. Oh, I forgot to close off that parentheses there. And now let's go ahead and distribute that 3. So 3a squared plus 6ah plus 3h squared plus 2a plus 2h minus 3a squared minus 2a all over h. So we should see several expressions canceled. My 3a squared canceled, my 2a's canceled. So what are we left with here? The limit as h approaches 0 of 6ah plus 3h squared plus 2h all over h. And we're going to move this party up here. We're going to simplify this. Each of those expressions in the numerator. This is not 6a plus h. This is 6ah. I'm not sure what I was thinking here. That is 6ah. We're going to divide each of those terms by h. So I am left with the limit as h approaches 0 of 6a. 3h squared divided by h is 3h. 2h divided by h is 2. And now I'm going to substitute 0 in for h. Just like we do when we evaluate limits, we use direct substitution. Make sure you don't substitute in for a. We only substitute in for h. So 6a plus 3 times 0 plus 2 leaves us with 6a plus 2. So what did we really just find? We just found an expression for the slope of our tangent line. Now that you have this expression, you could use this to find any slopes that you want. So for example, let's go back and test it. My part A on example number 2, I was finding the slope of the tangent line when A was equal to 3. Now come on down here. Let's substitute 3 in here. 18 plus 2 is 20. Sure enough, we got the exact same slope that we got up here. So this is when A was equal to 3. What if I changed the story and instead I made A equal to 1? Like the other example up here that I skipped over because I didn't feel like doing this whole problem again. If I were substituting A in, we'd have, a 1 in, we'd have 6 times 1 plus 2. So we'd have 6 plus 2, which is 8. So evaluating this limit formula with A really leaves you with something a lot more powerful than just a numeric answer. It leaves you with an expression to represent the slope of the tangent line, which can then be applied towards any x value that we want along the curve itself. Okay, so we're going to take this idea of definition 2 and we're going to build on that one more time. So on the next page, we are talking about velocity and other rates of change. Last thing we're doing today. So in section 2.1, we're going to skip the bell work question. That was just a problem that you guys had in your homework. And we're talking about the problem that we did in the beginning of chapter 2.1, where we dropped a ball from the CN tower, and we were trying to find its velocity at a certain time value. In fact, we were trying to find the velocity at 5 seconds. Now, let's take this idea of a tangent line, which represents velocity. We know that from earlier in chapter 2. And so, as in the example of the falling ball, we define the velocity or the instantaneous velocity, v of a, at time t equals a to be the limit of the average velocities. Remember, average velocities is the slope of the secant line. Instantaneous velocity is the slope of the tangent line. So the slope of the tangent line formula that we used earlier, this was this definition 2. We're now going to use that to represent velocity. And if it's a limit, then I'm going to actually call this velocity. And you'll see me put a little INST for instantaneous. And this means that the velocity at time t equals a is equal to the slope of the tangent line at p. So what we're going to do when we work this problem, we are going to work smarter, not harder. We're not going to substitute a specific value in for a or for x, because a is representing an x value. We're going to evaluate this with this a plus h and this f of a in there, so that we get a formula that represents slope of the tangent line, and hence a formula to represent the instantaneous velocity. All right, so look at the example. Suppose that a ball is dropped from the upper observation deck of the CN tower, 450 meters above the ground. The distance fallen by the object after t seconds is s of t equals 4.9 t squared. All right, that should look familiar. We did this exact same problem earlier in the chapter, but we did it with a calculator. So for part A, the question says, what is the velocity of the ball after 8 seconds? It's implied they're talking about instantaneous velocity. If they want an average velocity, they would have to call it an average velocity, which would be the slope of a secant line. So I want to use the limit of f of a plus h minus f of a all over h. So we're going to set up my velocity, my instantaneous velocity, is going to be the limit as h approaches 0 of f of a plus h minus f of a all over h. And so I am going to now apply my actual formula. So to find f of a plus h, I need to substitute a plus h into this position, or in this case, it's distance fallen formula. So on the front end, we're going to have 4.9 times a plus h quantity squared minus, oh, let me close that off. So this represents f of a plus h minus f of a. So I'm going to substitute a in here. So 4.9a squared. And that is all over an h. And now I'm going to clean this up as much as I can. And hopefully I'll be left with a formula to represent instantaneous velocity. So let's expand this quadratic out. So a squared plus 2ah plus h squared minus 4.9a squared all over h. 4.9a squared plus 9.8 ah plus 4.9h squared minus 4.9a squared. Let's keep going. Add like terms. We're seeing the 4.9a squareds cancel out. So what am I left with? 9.8 ah plus 4.9h squared all over h. And I can now divide both of these terms by h. So I'm left with 9.8a plus 4.9h. All right, so don't forget, oh, so sorry about that. Don't forget, we have to still evaluate the limit. And we could not do direct substitution earlier because we'd have a 0 in the denominator. So what we're going to do now is substitute 0 now that our denominator has simplified away. So what we are left with is 9.8a plus 4.9 times 0, which leaves me with 9.8a. What did we just find? We just found a representation for the instantaneous velocity. Whoops, there should be an I in there. Instantaneous velocity, which is the same thing as the slope of a tangent formula. All right, so this is going to be super helpful for us. Let's continue on. So what is the velocity of the ball after a seconds? We just created a formula for that. Part B, what is the velocity of the ball after 5 seconds? That just means we're going to plug 5 in here. So I'm going to find v of 5. So 9.8 times 5, which is 49.0. We're going to throw some units on there. This is a velocity. Remember, that's a rate of change of your distance over your time. And our distance unit is meters, and our time unit is in seconds. So this is meters per second. Here's my second answer for part B. And then the last question is, how fast is the ball traveling when it hits the ground? How fast is the ball traveling when it hits the ground? Let's think about what we know. So we've got this tower, right? I'm going to try to use my powerful artistic skills here. You have this tower, and there's an observation deck, and you drop this ball off of the tower. What do I know about it when it hits the ground? Well, they told me that, I don't know the speed yet, but they've told me that the tower is 450 meters above the ground. So the distance that this has traveled at this exact moment is 450. So I have two formulas I'm working with. I have a distance traveled formula, and I have a velocity formula. I don't know the velocity at this moment, but I do know the distance traveled is 450. So I'm going to work with that distance traveled formula. And the distance traveled is 450, so I'm plugging that in not for time, but for position. And we're going to definitely use our calculator here. So we're going to divide both sides by 4.9. And we are left with 91.8 equals t squared. Let's take the square root of both sides. Don't forget we get plus or minus. Take the square root of that number. And we're left with 9.58. Now that's a time value. That's in seconds. So does it make sense that we would have both a positive and a negative answer? Well, time doesn't really start until that person drops the object. So in this application, negative time values do not apply. So we can throw that out. So our time value is really going to be 9.58 seconds. Now, did we answer the question? How fast is the ball traveling when it hits the ground? We didn't. But we just found that it hits the ground at 9.58 seconds. Now that I know the time value, folks, the time value is representing your input, which is representing A in my formula. So now I can grab my formula and I can evaluate my velocity at 9.58 seconds. So it would be 9.8 times 9.58. And I do recommend that you not use that rounded number. I would recommend that you use the exact answer. So I'm going to just go up and grab that exact answer there. And I am left with a velocity at 9.58 seconds of 93.9 meters per second. Okay, so now I know this was a long lesson. This was stretched out over 2 or 3 days in your class, but we talked about 3 things. We talked about definition 1, which uses this formula here. It's wonderful and it's more simplified, an easier expression to use than definition 2, but it does not always work, meaning that you don't always wind up with a limit that you can evaluate algebraically. So then we learned how to use definition 2, which will always work for us. And then we applied definition 2 to a velocity problem. All right, thank you so much for listening. I wish you all the best.